Okay, so this is the sixth video on module theory. Recall that last time I was talking about the five limb. So continuing in that way, in this video or maybe in the next two videos, I'll be talking about what's called the snake limb. So let's see, we only need the notion of the exact sequences to understand the snake limb properly. Okay, so so here we suppose we have two short exact sequences. So for example, suppose you have one sequence as 0 to A1 to B1 and then C1 to 0. And suppose you have another short exact sequence A2, B2 to C2 to 0. Okay. And you have such nice maps between these two short exact sequences. Suppose you have this map A and then you have this map G and then you have this map H. Such that both of these squares are commutative. Okay. So now I can extend the short exact sequences in vertical direction, both up and down, by just taking the kernel, right? Uh, I was talking about it in the exact sequence video that we can always extend such exact sequences where the then this map is just the inclusion. So it is injective. So this is exact, right? And again we can extend here to the co-kernel. So I was talking about those things in the first video or in the I think the third video where I defined what are exact sequences and how to produce such exact sequences. So maybe you can check that video. Okay, so similarly you can do it here where these maps are the natural projection map. Okay, and same thing you can do. You have to take this kernel of G and this kernel of um, so this is the kernel of H, right? And this is kernel of H. Okay, and you can extend it to 0. Anyway, we don't need that 0 on top, so you can remove it as well. But okay. And suppose you have this map between A1 and B1 is alpha 1. Let's call it alpha 2. This is beta 1. And let's call this now beta 2. Okay. So now observe one thing first. You can consider the map alpha 1 from kernel of it. You can restrict the domain of that map alpha 1 to kernel of it. That you can do. So then maybe I can talk, I can uh, indicate it by alpha 1 tilde. So this is just alpha 1 with a restriction that the domain is kernel of it. And let's see what is the image. Let's find out the image. So now to find out the image, let's see. So take an element alpha 1, take an element from the image. So it will be alpha 1 tilde of some element x. So x is coming from kernel of f. But that is same as alpha 1 x, right? And then if you apply g to it, we'll get g alpha 1 of x, right? And then because this diagram is commutative, that is same as if you apply f first and then alpha 2. Right? But x is coming from the kernel of f, so this will give you 0. And then you get that alpha 1 tilde of x is in kernel of g, right? So this alpha 1 tilde actually induces a map from kernel of f to kernel of g. Right? So we can talk about this map, right? Because the domain and codomain makes sense in view of this the thing we already showed. And similarly, we can do it because this diagram is also commutative, so you can talk about beta 1 tilde. Okay, so I'm not doing it again. And now let's see. So again, you have co-kernel of F. So let's see if we can induce some similar sort of map using alpha 2 to get a map between co-kernel of F to co-kernel of G. So firstly, co-kernel of F means that if F is a map from A1 to A2, then the co-kernel of F, this is just A2 modulo the image of F. Okay. So now you can define this map. Again, this map is pretty much natural. You can define it as so this is from co-kernel of it. So any element would look like right because this is the equivalence class. You can take just a representative of that equivalence class and map it to, because A2 is coming from capital A2 and we have this map alpha 2 from capital A2. So you can do this, right? This will go to uh, say this. So my claim is this is the map from co-kernel of A to co-kernel of G. So this will be this thing is in G, right? Or I'm sorry, this thing is in B2 and this should be image of G, which is B1. Okay. So because we are talking about equivalence classes, we also need to take care of the well-defined property, because it may happen that some two representatives will map to some two other representatives, right? But let's see if that is the case or not. So for that, what you do is just take two such equivalence classes. So let's see, call them A2 and A2 prime. Okay. So they represent the same equivalence class is equivalent to saying that their difference is in image of F, right? And then because so you can so we need to show that this alpha 2 of A2 and alpha 2 of uh, A2 prime represent also the same class in the image of G in view of that, right? So let's just apply alpha 2 to it. And so you get this. And because this will belong to alpha 2f of A1, right? But again, due to commutativity, alpha 2f is same as if you apply alpha 1 first. So let's see, we're using commutativity of this square, right? So you're doing alpha 2 first, oh sorry, f first to come down and to go right. And you can do it by applying alpha 1 first and then g, right? But this is in image of g, right? Because this is this. So this should belong to this. And that is what we need. So this class is same as this class, right? You can take the tilde because this map suggests the alpha. Okay. So we get this is actually a well-defined map from kernel of A to kernel of G. So let's call this by alpha to tilde. Similarly, you can do the same for beta to tilde. Okay. So and you can extend it to zero. And we don't need zero. So let's bother about it. And now my claim is that so you have such a diagram where you have uh, two short exact sequences. Let's call it row 1 and you have row 2. Okay. So these are short exact sequences and using the commutativity of those maps F, G, alpha I and beta I, H, using all of that, we have managed to extend the top row, that is the first row, to produce another sequence. We don't know whether this is exact or not. Keep that in mind. We don't know if that is exact. We have not said anything about exactness. All we said is just these type of maps we can induce with those given information. And similarly here, we have again no idea whether it is, we don't know if it is exact or not. Okay. So now the main thing comes into the picture. That is, so now, so you have such a sequence from 0 to kernel F to kernel G to kernel H. We so far don't know whether it is exact or not, but we'll show that this is indeed the exact sequence first. And not only that, we'll also show that this kernel of H can be mapped, or you can produce a map to this co-kernel of H. Let's call it by delta. This is called the boundary, or sorry, this is called the sometimes called the connecting homomorphism or attaching homomorphism. So you are connecting kernel of each to the co-kernel of each. So this is something like, this looks something like a snake. So this existence of such a map, such that now if you just consider this map is there, I have not proved whether such a map exists or not. But suppose we have managed to prove that one such homomorphism is there between kernel of H to co-kernel of H. So just if you just remove all of those rows in between, so you get a sequence uh, kernel F, kernel G, and kernel H. Now here it is the map we are interested in. So this will take to co-kernel of F, and again we have this co-kernel of G and co-kernel of H to Z. Okay, so now we got a sequence of homomorphisms and modules. Now my claim is we will get this this sequence will be exact. Okay. So firstly we'll need to show that this part is exact. So this map is alpha 1 tilde, this is beta 1 tilde, and this is alpha 2 tilde, right? This is beta 2. Okay, so we have a lot of things to prove here. Firstly, we need to show that image of alpha 1 tilde is same as kernel of beta 1 tilde. That is number one, to show exactness at this part, at kernel of G. And also we need to show alpha 1 tilde is 1 right? To exactness, to show exactness at this stage. And beta 2 tilde is subjective. But those two, these things are easy to prove because we have already had this alpha 1 is subjective and beta 2 is, alpha 1 is injective, sorry, and beta 2 is subjective because these row 1 and row 2 were already given to be exact. So these are not very difficult to prove. So maybe I can leave it. Now, the main thing we need to show that the image of beta 1 tilde coincides with kernel of this uh, connecting homomorphism, and then again we need to do the image of, or I should say kernel of alpha 2 tilde matches with image of this delta, and moreover image of alpha 2 tilde matches with kernel of beta 2 tilde. So we need to show everything. So we need to show all of them. Maybe I can leave these two things. These are not very difficult. So apart from that, we need to show four things. But even before proving, we need to define such a map delta for which these two properties are true. So let's see. So firstly, we don't need to define delta to prove this one and this one, right? Because these are already there. We have already shown that such alpha 1 and beta 1 induces such alpha I tilde and beta I tilde, right? So we don't need any delta. So let's see if we can do it. So maybe I will talk about the definition of delta and to prove how this image of delta matches with kernel of alpha 2 tilde and these two in the next video. So for that I need to define what is the map delta. So I will maybe I can do it in the next video. Okay, so for now, let's see. So firstly observe one thing that we have already had this information that image of alpha 1 is same as image kernel of beta 1. That is from the fact that row 1 is exact. Okay. So in particular you get that uh, if you apply beta 1 to any element of image alpha 1, you will get 0, right? And so if you consider these maps, this will imply again simply that this is true, right? Because these are restriction of those alpha I, alpha 1 and beta 1. That is easy. So from here you will get only one part, that image of alpha 1 tilde lies in kernel of beta 1. So yeah, we get this. So remember we are proving this one. So from here we get uh, one side of that equation. Okay. Now to prove the other part, let's see. So suppose we pick an element from kernel. So we need to show kernel of beta 1 tilde lies inside the image of alpha. Okay, so just pick an element from kernel of beta 1 tilde. Okay. So now coming back to the diagram, let's see. Uh, yeah. So we are at here, right? So now let's see. So because it is in kernel of beta 1 tilde, it will just take x to 0. And that is because this is just a restriction of beta 1 map. So you can con consider the map beta 1 itself. And now, because this is in kernel of beta 1, and due to exactness, this is same as image of alpha 1. Right? So, I can lift this x. So, x was inside kernel of beta 1. Right? And now we are taking it to some alpha 1 of y. So, because x is in here and kernel of g is anywhere inside b1. So we can take consider x here, and from alpha 1 we get pre-image y inside a1. Okay. So that's about it. Now then, let's see how we can manage to do. So we need to find a pre-image under the map alpha 1 tilde, right? So alpha 1 tilde is nothing but the map alpha 1. With the extra property that the domain is just the kernel of it. So here we have already got an pre-image under alpha 1. So only thing we need to consider, we need to show that this y belongs to kernel of f, right? Because if we can manage to show, then alpha 1 tilde of y makes sense because alpha 1 tilde is the map going from kernel of f. But that is same as alpha 1 of y, and we get this. Then we would be done. So only thing we need to show is that this is in kernel of f. So let's see how we can do it. So just apply f of y. You need to show that f of y is 0. So so we need to show that f of y is 0. So let's see where it takes. So suppose it takes f of y to some element inside A2, right? Here. And now we can apply alpha 2 to it. Remember alpha 2 was injected. So applying alpha 2 and using the fact that this square is commutative, so you get uh, same as applying g and then alpha 1 of y. But clearly this is 0, right? Because x was coming from kernel of beta 1. So remember, kernel of beta 1 means this is inside the domain of beta 1 tilde. So this is inside actually kernel of g. And so because that is x, so g of x will be 0, right? Because this is inside kernel of g. And due to the fact that alpha 2 is injective, so alpha 2 f of y 0 implies actually y belongs to kernel of f. So we are done, right? So we have been already managed to prove this part 1. So yeah, so already we have been able to prove this. So that ensures exactness at this. I have left these two things to show that exactness at kernel of f and also at co-kernel of f. I'm not doing this. And now let's see if we can do exactness at this. Right? So again, the basics. First thing will be easy because then again. So remember this alpha 2 and beta 2 inducing the map alpha 2 tilde and beta 2 tilde, right? And so already we again have alpha beta 2 composing with alpha 2 will give you 0 because of the exactness of the second one. And so you can just take the tilde from there. So you get, or maybe let me just do it again for you because I have left this part the last time. So let me do it here. So what we need to show, so this is what we are looking to prove. So first, take any element from the image of alpha 2 tilde. So now we need to take care of the domain and codomain. Okay, let's see. So alpha 2 tilde is a map from co-kernel of it. So any element of alpha 2 tilde will be some A2 plus image of it. Okay. Now we need to show this is inside kernel of what? Beta 2 tilde. Okay, so let's apply beta 2 tilde. So let's see. So first, this will be same as just applying alpha 2 to A2 and you get G of B1, right? This is first. And this is same as applying beta 2 to the first element which is alpha 2 of A2 and then you will go into H of C1, right? Because beta total is a map from co-kernel of G to co-kernel of H. So this is the image of H. And now, as I said, the second row was chosen to be exact. So this will result in 0, and that belongs to the image of H1, anyway. Image of H of C1. Sorry. So this will give us just the class of 0. Right? Oh, so this easily shows that image of alpha 2 tilde is inside kernel of beta 2 tilde. That is half. And again, we have to show the other one. This one we did not really do anything. We just used that this is 0. So that was the easy part. So again, we got the half intuition. So let's see. Again, we need to show the kernel is contained inside the image. Okay. So how we can do? Let's see. Um, so again, just pick any elements from the kernel of beta 2. Let's do the usual thing. Let's go the usual flow. So so kernel of beta 2 tilde is co-kernel of, oh sorry, domain of beta 2 tilde is co-kernel of G. So any typical element from the domain would look like say some element of so remember G was a map from let me see, B1 to B2. So any element would look like some, let me just take it X plus G of B1. Right? Let me just take this from kernel of beta 2 tilde. So this implies if we apply beta 2 tilde on that element, it will go 0. Right? So this is just this plus h of C1 and this is 0. 0 means this is again h of C1, right? Because 0 under this 0 inside co-kernel of H. So this is just H. And that implies that beta 2x is actually inside this image of H. So you can consider some y, right? So again, let's go back to the diagram. So we got beta 2x is h of 1. Oh, so uh, okay, hold on, just let me remove this one. Let me remove this. Okay, okay. So here, just a second. Yeah. So x was what? Let's see. So x is inside the co-kernel of G, right? So x is an element here, right? And we get beta 2x. So beta 2x will go inside C2, but so okay, but that has a pre-image under H. So that is beta 2x, and that can be lifted to some y under this map H. Okay, so so we are at C1. Yep. And what did you remember what we were looking to prove that this element x plus image of G is inside image of alpha 2 tilde, right? So alpha 2 tilde means we need to somehow go to A1, right? Because then it will imply that you know. So let's see. Let's not get too much confused with all of this. Let's see how we can do. So we get that beta 2x is h of y. Okay, and now so y was in C1. But remember, we can easily lift y to at least B1. Even if we cannot lift it to A1 directly, we can lift it to B1. That is easy because of the fact that beta 1 is surjective because their sequence was exact. So at least what we can do is that y can be lifted to some element, what I call it z. At least we can go backward halfway. That z is inside image of, oh sorry, z is inside b1. Okay. And now then beta 2 of x is the same as h composed beta 1 of z. Okay, so look again, let's go back to the diagram. Because and remember this diagram is commutative. So H beta 1 is same as beta 2 G, right? So you can consider this belongs to the kernel of beta 2. And that's what we needed because kernel of beta 2 is same as image of alpha 2, right? So we can lift this to the some element in the domain of alpha 2, that is A2. So let's see. So this Z, and we consider this element, this, right? X minus G of Z. And that can be lifted to some element A2. And that is what we needed actually, right? Because then X, because, so image of alpha 2, so let's see again. So then we get G, X minus G of Z will be some alpha 2 of, let's check what we called A2. Okay. And so now what we needed to do, we are almost there. So we needed to prove that this element is actually inside image of, so this element belongs to image of alpha 2 tilde, right? That is what we needed to prove. But then again, so this class of X is same as class of this element, right? Inside the uh, co-kernel of G, because x minus this alpha 2 of A2 is inside the image of G, right? So we're done just because we started with this element x bar. X bar is nothing but x plus image of G, and that is same if you write it as alpha 2 tilde. So we got this pre-image as A2, and that is f of what was it, A1. So we get this as a pre-image under alpha 2 tilde. So precisely this is the pre-image, and this kernel. We started with an arbitrary element from the kernel, and we learned its image, and that's it. Okay. So, so we have established the exactness at this point also. So the only remaining thing is to prove the exactness at here and here. But to prove this, we have to define the what is called the connecting map, the delta. So I will define it in the next video and also show the exactness. And actually, this snake lemma is very much useful in homology theory, where you just have what is called a chain complex. So suppose you have a short exact sequence of a chain complex. Remember, I defined chain complex in the exact sequence. So there you have such infinitely many modules, say, a sequence of modules and a homomorphism, where that is not completely exact, but you have, if you compose two such maps consecutive, uh, then you will get the zero map. So you have only one part of that inclusion. That so if you just maybe I can write it here. So remember, a chain complex is such a map. Let's call it say mi to mi plus one to mi plus two, and so on. This is say m1. This is m0. Suppose these are this is a chain complex. If these di satisfy this property, so you apply di first, you go to mi plus one, and then you apply di plus one. That is a chain complex. Okay. Suppose we have three such chain complexes. So I can denote it by say scripting. Suppose you have three such chain complexes. Say suppose you have A, B, and C. You have these three chain complexes, and you have a short exact sequence between these chain complexes. So this is nothing but such AI, right? With if I denote it by this. Okay. And this is nothing but BI, if I denote it this, and this is nothing but CI. Okay. So now, what we get? And we have a short exact sequence like this. So let's call it phi, let's call it psi. So at any nth level or at any ith level, there is a short exact sequence, right? So let me just take AI to BI to CI to 0. So this is a short exact sequence of chain complex, remember, where each ABC are denoting just a chain complex. And you have this map, let's go with the notation that is phi and that is psi. So you have a such a short exact sequence. And you have again a short exact sequence at the next level. Okay. And this is just this, this. So and from here you can take this image of this is inside this, right? So we can talk about the quotient module, this, right? Because this makes sense. This. And this is what is called the homology group at the ith level of that. So the module, right? So for any module, you need to find such a uh, chain complex and then such nice attaching maps, such that sometimes it is, if you just ignore the indices, sometimes it is called d square AC. And it should be understood from the context that d square does not have a particular meaning, but this d square means that if you compose these two consecutive maps, boundary maps, you will get zero. So this is the homology. So and yeah, so using Snake Lemma, what we do is suppose that you have these maps, right? This is just DIA, this is DIB, and this is DIC, right? And again, you have this going up and down. So now what we can do, you can talk about the quotient at each level. You can talk about the quotient at here, then quotient here, then quotient here. Then using the Snake Lemma, we can induce such a map from this homology group to this homology. I mean homology group at this level to homology group at this level. So that what that will do, that will just take uh, that will just make these short exact sequences into a long exact sequence, because once you are here, then again using the boundary map you are going here. Again you can apply the boundary map to go here. So you are not stopping at just here. So this helps to define such a long exact sequence in any homology. Or similarly, if you just dualize it, or dualize means if you take the home functor, then you can get the cohomology. That is exactly same, but the arrows will go in opposite direction, because this home functor will be a contravariant functor. So I'll come to this those things later. So I'm just saying why this snake lemma we use. So yeah. So in the next video, I will define this snake level, the snake map, or the what is called the connecting map delta, and we will see exactness these two positions here and at here. So let me stop.